Welcome to your first AP Calculus class. By the time you watch this video, you should have read the section and rewritten these 5 objectives in the form of questions, and then written your notes and tried to answer those questions. And so hopefully through that process, you realized that the skills that you have been developing over the past several years, from your pre-algebra, algebra levels, all the way to the present, that those skills are now going to be used collectively as you consider equations. And you might be wondering, well, why is this section so important? Why did the author say this is the very first section that you need to know that you have a good foundation in before you can move on to AP Calculus? Well, one of the reasons for that is because everything that we experience in life, that we can touch, motion that we can see, phenomena that we can watch occur, we can write equations for all of that. So absolutely everything in life is an equation. And so as we move into calculus and we start studying more complex ideas and looking at the life around us and trying to express that mathematically, then graphs become very important. And so when I look at an equation, the very first thing that I want to notice is, well, what does that thing look like? And so I'm very interested in its shape. Look at the cartoon over here. So we're looking at the dance moves, and you guys did this in pre-cal, and you might have thought I was crazy at the time that I made you do it, but what was the reason for that? It was so that you would have a very instantaneous connection, that when you see a math equation, a shape comes along with that. You've got to know what the equations look like. We also want to know where they relate on the coordinate plane. Where do they live? What is their placement? And so you want to know what are the x and y values that pair up together to put that on the coordinate plane. In addition, we also study how they behave, and we know that behavior is slope. So we're looking at is it very steep? And what's it doing is it moves left to right, right to left, from the center out to the edges. Are there any type of curves and extreme things that happen as we are watching this graph move on the coordinate plane? And then we also want to be very, very careful about any problem areas that might show up. So remember the problem children in algebra, the ones that would cause your equations not to exist. No negative values inside radical, because those are imaginary, and no zero denominators. So we want to make sure that when we look for problems, we're always looking at our domain. We want to know, where does our x values exist? What x values do we need to eliminate? Because what occurs when your function fails to exist, those are where you get your holes, your asymptotes, and gaps in a function. And those are very critical things to know as we go on and study graphs. So take a moment and do a quick self-check and see if you can sketch the 6 basic algebraic functions by hand without peeking. Okay, I'm not going to know, but you're going to know whether or not you know it. And when you find things that you don't know, then that's what you work on, and that's what you start memorizing. So do the algebraics and then challenge yourself. Do the transcendentals, the trig, the exponentials, and the logs as well. So pause the video, and then when you're ready, come back and check and see if you got it right. So welcome back. Let's check. We have our constant function, which can be anywhere on our graph. It's a horizontal line depending on what value of your constant that you have. You have your straight y equals mx plus b, the little cup shape for your parabola, the spaghetti noodle for your cubic, the victory sign for your absolute value, and the little ballet arm for your square root. And data in real life doesn't always just mirror one of these. It can be a combination of algebraic and trig, algebraic and exponential, and or anything. And so by using our basic operations, we can make an infinite number of functions to meet whatever needs we have. And just be careful that when you're dividing, protect your domain. And we also have function composition. Remember, the notation has two different forms, but they're exactly the same, where you put one function inside the other as the variable. So check it out, make sure that you know it, and let's move on. Now we're going to talk about different methods of graphing. The first method we're going to look at is graphing by plotting points, because it's the very first method that you learned. You know that this requires you to make an X and Y table, and you want to pick points that are going to make your life easy. So I'm choosing values of X that are going to cancel my fraction when it comes out of that absolute value. It's basic math. -6 plugs in for X. -6 plus 2, -4, absolute value, +4, multiply by the -1/4, -1, -1, minus 3, -4. So when X is -6, Y is -4. You guys get the idea. So moving on, we have -2 is X, we get -3 for Y. When we plug in 2 for X, we get -4 for Y. And when we plug in 6, we get -5 for Y. So then we're going to plot our points. We have -6, -4, -2, -3, 2, -4, and 6, -5. Now, let's pretend for a moment that I have no idea what graphs look like. And so if all I have to go off of is points, well, then I can actually get very creative. And I can put curves where I want, and I don't know, I don't have any other points on here. I only have these 4 to guide me. So if I'm graphing by plotting, did I really do anything wrong? But we all know that this isn't the picture of this graph. So again, most important, know what it looks like, and then your points will guide you, although not really a perfect method. So by now we know that graphing by plotting points, not exactly your most effective method because there's so much room for error, but there are things that you can do to protect yourself. Like, for example, finding your X and Y intercepts. So if I want to find my X intercept, I'm going to set the Y value equal to 0, setting my equation equal to 0, solving for X. I'm going to add the 3 and multiply it by a -4 to get my absolute value isolated. So I get -12 on the right, and an absolute value can never be equal to a negative. And so I know that there are no X intercepts. And then looking for my Y intercept, all I have to do is let my X value equal 0. And so a +2 times a -1/4 is -1/2, and adding that to a -3, I get -3.5, -3.5, as an extra point that I can put in. So now I know that I have a y-intercept right here, which guides me a little more, and I bring in that knowledge of that this is an absolute value, and so my vertex is right at the -2, -3 mark, and I bring that down. And there's the graph of my absolute value. So we were able to accomplish it by plotting points, but not exactly all that effective by itself. So we'd want to look and see, well, what other tools do we have available to us, because we obviously need to enhance this particular method. A more eloquent way of graphing is graphing by shifting. This is why we spent so much time memorizing what the shapes of graphs were, because that's the first skill that you need. You need to be able to look at a graph and know what is its basic shape. And then looking at the math that occurs within the equation, then that causes different things to change. So the first thing that we look at is our pattern. So we have a basic pattern for every function. They all follow the exact same pattern. Math is so wonderful that way. And so we identify our parent. We're dealing with a basic absolute value x. So I'm going to graph that first. so that I have my starting point. And then I'm going to read the changes as they occur from left to right in the graph. So the first thing I notice that's different from my original, because see, there's no negative out front, is that negative in front of the 1/4. And so this negative value gives me the clue that this is a reflection. A reflection is a rigid transformation. It doesn't change the size or shape of the graph. It simply moves it in its pure form. So it's a reflection across the x-axis. Had the x been negative inside the function, then that would have been a reflection across the y-axis. So just making my first change in a dotted line, there's my reflection. Okay, so the next change that we see is the 1/4 out front. And that's a multiplier. Now, taking a fraction of a function means you're making it smaller than it would have been. I'm only taking 1/4 of the actual values that were originally there. And so this is a vertical shrink. Had that number been greater than 1, it would have been a vertical stretch. And a vertical stretch approaches the y-axis, where the vertical shrink approaches the x-axis, because it makes the y values only 1/4 of what they would have been. Our next change is the 2 inside with the x. Now look at our pattern. See how it says x minus h? Because it says x plus 2, that tells me that that 2 was a negative 2, because minus a negative 2 makes that plus sign show up. So negative 2 means that this was a horizontal shift 2 units left, because it's negative. So the vertex is normally at the origin, and it just moved 2 units left. And it's still 1/4 of the size, and it's still reflected. The very last thing that I see is that negative 3. Now the negative 3 tells me that this was a vertical shift because it's outside, and that it shifts down 3 units. So taking my vertex from where it's at, I'm going to move down 3 units, and then I keep the reflection and 1/4 of the size, and that's my final graph. So in pre-calculus, I made you show all of these steps so that you would have a very solid foundation on knowing exactly what numbers did what, and you could get the graph drawn correctly. Now in AP Calculus, what I expect you to do is simply be able to look at it and graph it. All of this part, the original function, all of the shifting, you no longer have to draw that. You should be able to look and come straight to your final function and move on, because this is just a tool to use. We've got bigger and better things to do, so let's get going. Another important tool that we use in graphing is called graph symmetry. So graph symmetry helps us because it makes our work faster. If I know that I'm looking at an equation that has symmetric properties, then I really only have to worry about getting 1/2 of the graph really accurate, and then knowing where that line or point of symmetry is and reflecting it in its appropriate place. And so it makes the graph very easy to draw. So the first graph that I want to look at has x-axis symmetry. And what x-axis symmetry means is that any point that I have on my graph is going to have a reflection point across the x-axis, and we're going to call that reflection point P prime. So my original point P had a particular xy coordinate, and what happened as it went to its image point P prime? Well, my x's stayed the same, but my y's changed their sign. So your P x y is going to a point, reflection point, P prime, x negative y. So if I wanted to check an equation to see if it had x-axis symmetry, I would simply put a negative everywhere I see a y and simplify the math. If I end up with the exact same equation that I started off with, then it has x-axis symmetry. Now, y-axis symmetry. For any point P on my graph, then it should have a reflection point, P prime, reflecting across the y-axis. So for P, my original point, xy, what changed as we went to P prime? At this point, the x's did not stay the same, but the y's did. So I have a negative x, and whatever the x was, if it was negative, it's now positive, and if it's positive, it's now negative, but my y stays exactly the same. To test for y-axis symmetry, notice the notation I have. F of x is equal to f of negative x. That means I can put a negative anywhere there's an x, simplify the math, and I should end up with my original equation. Now, I have a quick question for you. Why was I not able to use function notation here for x-axis symmetry? Why didn't I write anything there? Answer that in the comments that you make at the end of this section where you turn in your homework. Now, moving on, we have origin symmetry. Now, origin symmetry is different than the line symmetries because it doesn't cut the graph in half and then flip it. What it does is it breaks the graph at the origin. So right here at the origin, that's my point of symmetry, and I should be able to rotate my graph, break it and turn it, and it should fall onto itself on 180 degrees around the point of the origin. Now, if I shift this graph has origin symmetry right now, but if I shift it up or down or left or right, it's no longer symmetric to the origin, and I really don't care about any other points on the graph as far as symmetry goes. So the only point symmetry that we're interested in is origin symmetry. Okay, so I pick a point P, and I rotate it 180 degrees, and I find my point P prime. And so now what has happened to my original point? It has mirrored to a point P prime where both my x and my y have changed. And so whatever those signs were, just change them. And the test to see if you have origin symmetry is you take a negative and put it in with the x and simplify it. You take a negative and run it through the original function. You take those two new functions you now have, and they should be equal to each other. Up until now, we've talked about tools that help you graph. Now let's talk about using graphing as a tool to help you answer more complex questions. So I have two equations, y equals x cubed minus 4x, which I graphed in green, and y equals negative x plus 2, which I graphed in orange. And these two equations represent particles in motion that are traveling across my coordinate plane over time. And my question to you is do they collide over time? So I look at my graph to help me out, and I'm looking for places where their paths cross over each other. So I have a definite intersection right there, and it looks like it could be very close to -2. It might be between -2 and -3. I'm not really sure. And then over here on the right, there's another possible intersection somewhere around 1. And so I look at my equations and I say, you know, my graph, how accurate is it? Did my hand shake as I drew it? Or, you know, I'm writing on an iPad with a stylus, and you've seen the writing quality. It's not that great. So I'm not going to trust the graph. I'm going to go for a more analytical method. So using the method of elimination, I'm going to leave my first equation pure and run a negative through the second one. And I get 0 is equal to x cubed minus 3x plus 2. And it doesn't follow any of my sum or difference of cubes. So my basic factoring tools can't use that in this instance, but we do have that cute little technique that we learned in pre-calculus called P's over Q's. And so remember that your P's come from that constant term and that Q's come from the leading coefficient. So factoring that constant term, all of the possible factors, plus or minus 1, plus or minus 2, and factoring the leading coefficient, we just get plus or minus 1. So our final options are simply plus or minus 1, plus or minus 2, as we look at that as a fraction. Okay, so setting up our synthetic division, don't forget to put a placeholder for the squared term that's missing. And we start dividing. We look at our graph. Let's choose -2 as a possibility because it shows up so close in our graph and it shows up in our list. It looks like a really serious possibility. So -2 times 1, adding down, and then multiplying again, and adding down, and multiplying again, and adding down proves that x equals -2 is a solution to the system. So now what are we left with? Because we did the synthetic division, it broke our polynomial down from a cubic down to a quadratic. So using our new coefficients that we found, we have x squared minus 2x plus 1, and because it's a quadratic, we'll set it equal to 0 and factor it and solve. It's a perfect square trinomial, so x minus 1 squared is equal to 0, and we get x equals 1, which, yep, that's pretty much what we thought at the time. And the only different thing that we do see is that this is a double root. So now let's talk about what our answers mean. As we look at this and we say, okay, x equals -2, they did intersect here, but the problem is that negative time doesn't exist. And so we're not going to accept x equals -2 as an answer. We're going to eliminate it because it doesn't answer our final question, because over time, negative time doesn't exist. Now, let's look at our double root. Our double root says that the green graph came, and because it didn't cross, it bounced and went back. That's why the 1 showed up twice. Had it showed up an odd amount of times, they actually would have crossed paths over each other. However, because they do share that 1 point, they do intersect, and that means that they collided. They just simply bounced off each other and went their separate ways. So our answer is x equals 1, and if we plug that in to one of our equations, let's use the simplest one, we'll get -3 as a y value, and that is our final answer. And that is how graphs help us answer more complex questions. The other day, I had the opportunity to watch the Shark Tank show on television, and that premise of that show is where entrepreneurs come in and pitch their businesses to self-made billionaires so that billionaires can invest in the companies and help these companies grow. And so I'm going to give one of those scenarios to you to decide on whether or not you, as a shark, are going to invest in this company. So it's a cookie business, and the woman wants $200,000 as an investment. For that, you're going to receive a 3% equity. The cookies sell for $1.85 each. Expensive cookies, but supposedly they taste good. So anyway, she has 12 stores total. 8 stores are in Indiana. And she just opened 4 more stores in Florida. Now, last year's sales were $2.3 million. And this year, projected sales are $2.5 million. And she has in debt $800,000. Now, your task is, are you going to invest in this woman's business And you have to use concepts from this section to explain why or why not. Good luck! Now it's your chance to show me what you learned from this section. There's a form located below this video for you to fill in the answers to your questions. You'll notice that there's not enough room to show all of your work. Therefore, you need to make sure that that's written on paper and that you can turn that into me tomorrow to verify your work. All of the Google Docs forms need to be time dated in my Google Docs account by 6:30 tomorrow morning in order to receive credit. Good luck, and your assignment is coming up right after this. See you tomorrow. Finally, I wanted to make sure that you were clear on what was expected of you. So what you need to make sure that you complete tonight and get turned in as soon as possible is the 3 questions that get filled out on the form below this video. Those have to reach my Google Docs account by 6:30 in the morning. The assignment you see before you, I would like you to get started on it. If you don't have time to do it all, at least go through each section and do the hardest problems, or those problems that you think look hard. And then that way, if you get into trouble or you have any questions, you can ask me in class tomorrow and make sure that you're able to do that so that you can complete this assignment by tomorrow evening and have it ready for class the next day. Finally, there's a comment box that's optional at the lowest part of the form for the Google Docs account. I'd like you to put in there any comments that you have about the video lesson or any suggestions that you have. I'm really interested in your opinion. This is a completely new media for me, and I'm learning right along with you guys how this class is going to go. So we're in this together, and I look forward to seeing you tomorrow. Bye.